5.3 Part 2, Inverse Functions. Theorem 5.8 says that if f is a function whose domain is an interval, we'll call the interval I, and f has an inverse, then the following are true. If f is continuous, then its inverse is also continuous. If f is increasing, then its inverse is also increasing. Likewise, if f is decreasing, then the inverse is also decreasing. And finally, if f is differentiable at any certain point in the interval called c, and the derivative at that point does not equal 0, then its inverse is differentiable at c. But obviously then, if f could be differentiable, which means there's no sharp turns in it, no asymptotes, no jumps, no holes, but if the derivative would equal 0 at that point, at some point c, then f inverse is not differentiable at that point. So as long as f is differentiable and doesn't equal 0. So as long as c isn't an asymptote, a hole, a jump, a sharp turn, or doesn't equal 0. So it means that at a max or a min of our original function, then the inverse would not be differentiable there. So even at those maxes or mins where they have a high or a low point, like if our original function has a maximum there, then that tangent line, the slope would equal 0 there. So at that point, our inverse would not be differentiable. And also here, where the slope of the tangent line equals 0, if that point is called c for the x value, then that inverse would not be differentiable there. Theorem 5.9, the derivative of an inverse function. Again, f is a function that's differentiable on I. If f has an inverse function, we'll call it f inverse, then f inverse is differentiable at any x for which the derivative of the inverse does not equal 0. Does not equal 0. Then the derivative of the inverse, and that's this notation here, this means derivative of the inverse, is equal to 1 over the derivative of the inverse of x for any particular x. So again, f has to be differentiable, no sharp turns, no vertical asymptotes, no holes, no jumps. And it has to have an inverse, so that means it's 1 to 1, always increasing or always decreasing. And as long as when you put a number into the inverse and then put that answer into the derivative, that won't equal 0, then our derivative of the inverse will equal 1 over that value. And that will be helpful for times when we don't know the equation of the inverse, but you need to find the slope of the tangent line or the derivative of the inverse for some reason, but you can't actually calculate the inverse. So this formula you will need to know. I've seen it many times on AP tests as just a formula you have to know. Let's do an example. If we have 1/4 of x cubed plus x minus 1, and we're supposed to find the derivative of the inverse at 3, it would be nice if we could find the inverse function first, and then take its derivative, and then plug 3 in. But we can't. So we have to think about, we have the original function, and we have the inverse function. We're going to put 3 into the inverse function, well actually into the derivative of the inverse. So we're putting 3 in, that means it's our input. So for our inverse function, 3 will be our input, and we want to know what the output of that is, because we're going to use that formula right here, where if we're trying to find the derivative of the inverse at 3, we're going to do 1 over the derivative of the inverse function at 3. So this is what we're trying to find. So we're going to put 3 into our inverse. So if we put 3 in as our domain of our inverse, we're trying to find this number. What we do know is that the domain and range switch for the inverse and its original function. So if 3 is going to be the input, then it would have been the output of our original function. So what we need to find is the input that gives us an output of 3. And the reason we have to go through all this is because if this is our original function, we can't find its inverse. This is too hard to solve for. So what we can do, though, is find where this function equals 3. So we'll have 1/4 x cubed plus x minus 1, and we're going to try to find where that equals 3. Easiest way to do that is to plug that into your graphing calculator and find where this y1 would equal 3. So let's type in our equation. We have 1/4 x to the third plus x minus 1. And we want to know where that equals 3. So what I'm going to do is just enter 3 as the other function, graph them, and find where they cross. I'm going to find that intersection. So second trace gives me options to do intersect. First curve, enter. Second curve, enter. Guess, that's close enough. 2, 3. So x is 2. So my input is 2 when my output is 3 for the original function. So for the inverse function, if I want my input to be 3, my output is 2. So now I know that the inverse of 3 is 2. So I'm going to put a 2 there. So now I need to find f prime and plug 2 into it. So f prime of the original function, taking the derivative of this, is 3 times a fourth, so that's 3/4. Subtract 1 from the exponent, plus the derivative of x is 1, and the derivative of 1 is 0. So 3/4 x squared plus 1. Putting in 2, so the derivative at 2 is 3/4 times 4, that's 2 squared. So 3 plus 1 is 4. So that equals 1/4. So what that means is that the inverse of the derivative of the inverse at 3 is a fourth. So the slope of the tangent line of the inverse function at x equals 3 is 1/4. So I could now find the equation of the tangent line using the slope of 1/4 and the point 32. That would be the slope of the tangent line to the inverse function at 3. Again, if we could find the inverse of this easily, we wouldn't have to go through all this, but since we can't, and that will come up often in, at least once in AP Calculus on the exam, then you have to know this formula. All right? It will probably be on the chapter test and the quiz. So let's do an example here. If we want to find the derivative of the inverse at a, and this is our function, and a is -2, another example of the same type of thing. Our original function has an input and an output, and our inverse function has an input and an output. We want the input to go into our inverse to be -2, so I have to find the output. Well, that means that it would have been the output for the original function, so now I'm going to find the input. So 2x to the fifth plus x to the third plus 1. Where does that equal -2? Again, we'll put it on the graphing calculator. Oops. -1, -2. So the point -1, -2 is where these two cross. I mean, where if you put -1 into the original function, you'll get a -2. So that means if you put -2 into the inverse, you'll get a -1. So if I want the derivative of the inverse at -2, that equals 1 over the derivative of the inverse at -2. And now I know that the inverse at -2 is -1, so now I want the derivative at -1. So I take the derivative of the original function, 10x to the 4th plus 3x squared, plug in -1, so you get 10 to the -1, 10 times -1 to the 4th, 3 times -1. So that's 7. So we have 1 over 7. Make sure I did all the math correctly here. Oh, that should be 3x squared. Sorry about that. So 3x squared, so that's going to be 10 plus 3, that's 13. I hope you caught that before I did. So I checked my derivative, and that was what was wrong with that. All right. Another key inverse relationship is that the graphs of inverse functions have reciprocal slopes at their corresponding points. Remember, corresponding points would be like in that last problem at the point -1, -2. It corresponds to the point -2, -1 on the inverse. So this is the point on the original, and this is the point on the inverse. Okay, so the graphs of inverses have reciprocal slopes at corresponding points. So if we have the derivative of the original function, it would equal the 1 over the derivative of the inverse. So you could consider this to be the derivative of the inverse. Okay, so the slope of the original will equal 1 over the slope of the inverse. Okay, so if you know that the derivative of a function is 8x over 7, then this, which represents the derivative of the inverse, would be 7 over 8x, just that reciprocal relationship. So going back to this function, if this is the slope of the derivative, if this is the slope of the inverse at -2, then at -2, -1, then what would be the slope of the original function at -1, -2? The slope of the original function at -1, -2 would be the reciprocal of this, so it should be 13. Let's check that out. Okay, sorry. So the slope of, where was I? The slope of the original function at -1, which is the corresponding point to -2, -1, it's -1, -2. So the slope of the original function would be the derivative at -1, which we just figured out here is 13, so obviously it's the reciprocal. 1 over 13, 13. All right, so maybe that was obvious to you. Just wanted to walk through that with you. All right, another example, if we have f of x equals x squared for all x's greater than or equal to 0, and that's necessary because we only want the increasing part of x squared. Remember, x squared itself looks like this. But then we couldn't find the inverse because it's not strictly monotonic. It's not 1 to 1. It fails the horizontal line test. So if we just look at the part of x squared that is greater than or equal to 0, then it is increasing everywhere. So this part does have an inverse. So you can restrict the domain of functions to make them 1 to 1 or strictly monotonic, and then you can find its inverse. And the inverse would be the square root of x. So what we need to do is find the slope of f at 2, 4. So take the derivative of that. Notice that the point 2, 4 is in the part of the domain that we are including. So the derivative is 2x, and the slope is at 2 is 2 times 2, which also happens to be 4, which is not necessarily this y value. This is the actual slope of the point, slope at the point 2. And the inverse, which they gave us here, the slope of that, we need the derivative. So our original function is the square root of x, and the derivative would be 1 over 2 times x to the -1/2, which is 1 over 2 times the square root of x. And we want that, I should put inverse here. that's my inverse, at the corresponding point, which is the point 4,2, so I'm plugging 4 in. So the derivative of the inverse at 4 is 1 over 2 times the square root of 4, which is 1 over 2 times 2, which is 1/4, and it's the reciprocal. So just demonstrating that property. And one final example here about this inverse relationship with the derivatives. If we have the function cosine 2x, where x is between 0 and pi over 2, we want to find the slope of the inverse at 1. Finding the inverse of this is kind of tricky, so we're going to use that relationship that says that the slope of the inverse at 1 would equal 1 over the, I'm sorry, I want to use the letter A here. Oh, it took a lot away. Okay. Is 1 over the derivative. Wow. Of the inverse at A. So my original function, my inverse function, input, output, input, output. The inverse function, I want my output to be 1, so I need to find my input. Oops, I have that backwards. Sorry. So I'm putting 1 into my inverse here. So I need to find the output. So that's going to be the output there. So where will cosine of 2x equal 1? Do the inverse of cosine of both sides. Think about your unit circle. Where does cosine equal 1? Here cosine is 1. So 2x will equal 0 because the inverse cosine of 1 is 0 and the inverse cosine of cosine is 2x. Divide both sides by 2. X is 0. And also, this would be pi. That would be -1, so we don't want that. So just check in all the other places. All right, so then that's a 0, and that's a 0. So we need the derivative. Well, we need the inverse function, 1, which is 0. And then we need the derivative of cosine 2x. Do your chain rule. So it's 2 times sine 2x negative, because the derivative of cosine is negative sine, and the derivative of the inside is 2. So we have -2 sine 2x. So I keep forgetting to write that. Two times 0, we always do this part first, is 0, sine of 0, and then -2 times that. Here, sine of 0 is 0, so it equals 0. And that would be going in here, so we'd have 1 over 0, which is undefined. So this answer here is undefined. All right. Remember how to find the domains and ranges of f and its inverse, and then graph f and its inverse. If these are our two functions, this is f of x and this is the inverse. So domain, remember, domain is all the possible numbers we can put in. And since we have a fraction, the first thing you can think of is, we might have a problem in the denominator here because denominators can never equal 0. What would make this denominator equal 0? We better figure that out. Could this ever equal 0? Well, I don't know if you noticed, but x squared will always equal a negative number, a positive number, and if you subtract 1, you'll get a negative number. And the only way for x squared to equal -1 is if we're using imaginary numbers. but we're not. So this could never equal -1, which means that could never equal 0. So this function has a domain of all reals, which means that the range of f inverse would be all reals. However, we have this little add-on here that x has to be greater than or equal to 0. So our domain of f is, you can use interval notation, equal to, remember, is the included using the bracket, 0 to infinity, or you can say x is greater than or equal to 0. So how does that transfer to our range here? Remember I just said that the domains and the ranges switch. So you'd think that the range here would be 0 to infinity. Let's just make sure that makes sense. Can you put numbers like 0 to infinity here in this equation? Well, you can't divide by 0, can you? So how could that be the range? But could we have all the numbers other than 0, like 1, 2, 3, 4, 5? We could have 1, we could have 2, we could have 3, all of those. Are those going to be, oh, I'm sorry, I'm talking about the domain. You can't, yeah, sorry. You can't put 0 in for the domain, but we're talking about the range of its inverse. So could the numbers that come out of this be 0 or greater, including 0? Sorry, the range. So the numbers that come out of a square root. You could have the square root of a number that equals 0, right? Sure, you could have the square root of 0 that equals 0. And then all other positive numbers. So that range makes sense. How about the domain of the inverse? Well, we can do that two ways. We can look at the range of the original and switch it, or we can look at the domain of the inverse and put that in for the range, because they will be equal. So let's look at the range of this function. If we graph it, 1 over 1 plus x squared, we can quickly see what the range is. And we're only going from 0 to infinity. I'm going to make this y max a little bit smaller. So you can see our graph goes like this. So it's only between 0 and 1. It doesn't ever equal 0. It just kind of levels off. We can even zoom in a little bit more if you want to see that. Make our y min 0. Just bottoms out at 0, but it would never equal 0. This could never equal 0, because for a fraction to equal 0, the top has to equal 0, and that would never equal 0. So you can see that our outcome, our ranges, are going to be 0, but not including 0, up to, and then that, whoops, sorry, that max. What's this maximum value right here? If we trace it, we can see what it's getting closer and closer to, that y value. As we get closer and closer to 0, closer and closer to 1, including 1 at 0, when x equals 0, y is 1. So including 1. So that means that will be our domain of the inverse. So this is the domain of the inverse, this is the domain of the original, this is the range of the original, this is the range of the inverse. And let's just make sure that that range of the domain of the inverse makes sense. Can you put in numbers, not including 0, but everything up to 1, but nothing after 1? That makes sense, because anything after 1 minus that number would be a negative number. If we had 1 minus 2, we'd have a -1 on top over 2. So you can't do the square root of a negative. So demonstrating again that the domains and ranges of the function and its inverse switch. Last example, I promise. F of x equals 1/8 x minus 3, and g of x is x to the third. Let's talk about how to do composite functions with inverses. Remember, there are two different ways to notate composite functions. You could do g o f, little o there, of x, and that means that you're going to take g of x as the outside function and put f of x into it. Okay, so if we're doing this, what that means is we want to do the function f inside of g, and then that whole function we're going to do the inverse of it. So first of all, let's take f of x and put it inside of g. So we're going to take that and put it inside here where there's an x. So we're going to have something to the third power, 1/8 x minus 3 to the third power. But we want the inverse of that. So if that's our function, there's two ways to get the inverse. You can switch the variables. And then solve for y, so take the cubed root of both sides. So we have the cubed root of x equals 1/8 y minus 3, add 3 to both sides, cubed root of x plus 3 equals 1/8 y, multiply both sides by 8, so we have 8 times the cubed root of x plus 24 equals y, so that's our inverse function of the composite. F of g of x would be the f function with g inside it, so we're going to put that x cubed in place of x. So that's that. And then f inverse of g inverse, so we need the inverses of these two and put them inside of each other. So the inverse of f, if you switch the variables, so this is y, you're going to switch the variables, add 3 to both sides, multiply by 8, so 8x plus 24 is the inverse of f, and then the inverse of g, again we have y here, so we're going to switch those variables. So we have y equals x to the third, and we're going to switch the variables and then take the cubed root to solve for y. So that's the inverse of g. We want f inverse of g inverse, so we're going to take g inverse and put it inside of f inverse. So that would equal 8 times the cubed root of x plus 24. We're taking this g inverse and putting it inside of f inverse in place of the letter x. And last but not least, f of g inverse. So we do f of g first. And have we done that? Yep, that's this. So we want the inverse of that. So switch the variables, add 3 to both sides, multiply by 8, and then take the cubed root to solve it for y. So that's the cubed root of 8x plus 24. So those are all the fun things you can do with inverses and composite functions, and just make sure that you're doing them in the proper order. There's your final homework assignment. Have a great day.